Hello everybody, so I'm David Massart. Well, you probably don't know my company because we are really two people there, and what we offer is consultancy for whoever wants us to help them with their data or big data problem. So yes, and one of these customers is a company, it's called Mac. And what they do, among other things, well, they are a hardware maker, and one of their products is those traffic cameras. So just to understand how it works, so it's just a camera that will take pictures of a car, and then there's some kind of OCR embedded in the camera that will, based on photo, well, OCR, the plate number. The camera has also a GPS embedded, so they know the GPS coordinate of the camera and a timestamp, and they put this information in a message that they send. And well, usually all these cameras are really put in different places on the road and where the network connectivity can be poor. So the picture itself is usually not sent with a message. The idea is that each time there's a message, it's sent by the camera, but when the camera can send this message, and if the message cannot be sent, well, it can be kept in the camera for up to 7 days. So that's roughly the constraint we had to deal with. And if you look at the example of applications that you can, well, what you can do with this information, so basically a timestamp, a plate number, and a location. So you have things that's called blacklist, which basically you have a list of wanted cars. And well, when the wanted car is recognized, well, you know that the car was at some place, and you can send this information. So I've been surprised because you expect people being in part of this blacklist of wanted car to be relatively limited. So it's when I look at the list for the first time, I mean, you have Belgium, which is a relatively small country with 10 million people, and in this blacklist, you have 1.5 million cars that are registered. So it goes really from terrorists with high priority to people who are driving without a driver license or without insurance and all those things. So that's relatively easy. I mean, if you have one camera, you know you have this blacklist and you see the car, so you have things. You can do other things like speeding. If you have two cameras, it's also relatively easy. It's really a very simple math. I mean, you know the distance between the two cameras. You know, well, you know the time that the car, well, between two, well, a car was seen at one camera and at the other, and you know the speed limit. So you know if the average speed is higher higher than the speed limit or not. And so all this information like the blacklist or the distance between cameras and the speed limit, etc., that's part of a configuration that you have to add to the system. And then you have also things like overtaking, where you have another segment with two cameras, and basically it's a no passing zone, so you have to make sure that, well, if people follow the rules, the first car in must be the first car out of the zone. So that's 3 examples of things you can do with this. And okay, initially the system this company had, so they're a hardware company. They create the hardware. They create also, well, the software that runs this hardware that is embedded in the camera, and some applications for their customer. And so they started with a very standalone applications, which was a MySQL database that was receiving all the messages, and they were just operating on this database. And with a solution like that, they were able to manage up to 60 cameras. And so they came, basically there was the federal police in Belgium came last year and said, okay, yes, we would like to be able to manage all the cameras in the country. And so that's where they asked us to help them to scale up to 20,000 cameras, which is the estimate they want to have. And so, so here is the kind of solution we came. So the idea was to have some kind of something lambda-like architecture, and the idea of so between the idea of having a speed layer and a batch layer, and that's mainly that was the main reason for that was just to deal with these these network problem. So the idea was that when a camera is disconnected from the network, and it happens all the time, well, we wanted to be able to, first of all, when a camera is okay and just sending messages, you want to process these messages as fast as possible, and that's the role of the speed layer. And so when you have a camera that is disconnected, when the camera comes back and send all these old messages, you don't want these messages to interfere with the speed layer, so they're just sent to this batch layer where they can, they're persistent, and then you can batch process them. So it's just a security net where you make sure you don't miss any event, but also you use the speed layer to very quickly generate the events. And to generate these events, we put in place an event generator. So if you look at the diagram, so the idea is to have this iCar connector, which is just a way to manage the cameras and send the messages from the cameras to Kafka. And then Kafka is used to feed this event generator. And now I'm going to show you what this event generator looks like. Okay, so the idea of the event generator is really to have something that turns the camera messages into potential traffic violation events. You say potential because the machine doesn't say there's potentially a traffic violation, but it's the role of a human operator or a police officer to just validate if it's really a violation or not. And the idea is to have a solution that was extendable to support additional types of events. Not just the one I mentioned, but potentially new ones. So we wanted to be able to easily plug new types of events, and actually to be resilient to generate events without downtime, and to be elastic to adapt to the level of traffic. And to do that, we have implemented this event generator in Scala with basically a mix of Akka cluster and Akka streams. There's a nice library called Akka Streams Kafka, and we have heavily relied on that. Okay, so I don't know if you've heard of this Masterwork design pattern. So that was a source of inspiration, but it was a little modified. So in the original model, you have a master that receives messages that consist of a list of tasks and distribute the task between the different workers. Here it's a little different because we don't have a list of tasks really. Well, what we have is a list of functionalities more than tasks. And when a worker starts a task, it's a continuous task. It doesn't have a beginning of end. Basically, for the event generator, I mean, if you look at this worker one that does that process speeding, well, it's just taking events from Kafka, processing, generating the event, and sending them to another Kafka topic, basically. So when this task starts, it never ends. So the idea was more to have some kind of configuration, the task list, to give that to a master, and the master looks at, knows that he has to find workers to deal with a blacklist speeding overtaking. And so we use then workers. Each worker has a list of abilities. And, you have some kind of negotiation between the worker and the master to decide what to do. So the master, the workers are, master was definitely a character. Workers at a high level can be seen also as characters. And the idea is we wanted really to be able to add a worker, possibly with new functionalities, and add that to the network without having to change the configuration of the master. So the way it works is that the worker will just say, okay, yes, hello, we'll find the master and contact it. The master will answer. The worker will say, okay, give me some work to do, and here are the list of my abilities. And then the master will say, okay, yes, I have a task that you are able to do, or sorry, I have nothing for you to do at the moment. And if there is a task for the master, the master will ask the worker to perform the task. The worker will then start working on it and notify the master. And so starting to work on it, it's really connect to Kafka, start reading messages from the cameras, process them, and generate events. So that's the idea. Okay, so since we were using Kafka, we had to use Zookeeper. So the idea is really for workers to find to find their master was to rely on Zookeeper. Actually, we had plenty. The architecture was one of the constraints on the architecture. Is it had to be very flexible because it was sold to different customers. They are very they are mostly cities or municipalities or regions that have very specific constraint, and the architecture was had to be flexible enough to adapt to whatever constraint was requested by the customer. So, for example, when we deploy things in Brussels, they wanted to basically they wanted to have two data centers, and one of their big acceptance tests was, okay, we switch off one of the data centers and we want to make sure that the system resumes on the second data center. So the idea was for the master to have some kind of some kind of leader election using Zookeeper. So I don't know if you know how it works, but each candidate master actually will register in Zookeeper, get a turn, and Zookeeper it will, looking at Zookeeper, you can see which one of the master was the first to register, and it becomes the master. And so you can look at the list. And the idea was simply to include in the information that was sent to Zookeeper the address of the master itself, so that the worker interns were able to, by just looking at Zookeeper, to see what master was the leader, the elected leader, and well, find the address, and then it was possible to contact this master and start the little negotiation that I described. Okay. Okay. So now it's just looking at the way we have implemented the workers themselves, and here also it's so if you take actually it's better to start looking at these diagrams from here. So you have the worker here is that list of abilities, and the worker itself can be seen, I mean, it's really an Akka cluster. So I don't know if you're familiar with Kafka, but Kafka, you have a topic, so a queue, and this queue can have multiple partitions, and you need to have one client per partition in order to read all the data. So the idea was for the worker to have for each task to start to have a consumer group for Kafka, and to instantiate in this cluster as many instances as you have a Kafka topic on Kafka. So that was the idea. So the worker was just looking at his task, for each task, looking at the actors able to perform this task, and they were instantiated so that they could read the data. So one of the problems we had is, okay, so one of the ways you sort the data on Kafka to know on what topic the Kafka is sent is to use some kind of key, and the key we had was to use a plate number, which seems relatively natural. I mean, it's relatively easy. So each time you have a plate number, the idea is that the same plate number will always go on the same on the same partition, and so the same car, the information about the same car will always be processed by the same node, by the same actor, right? So that was kind of easy for the speeding, because you have all the information about the same car. It's fine. And for the blacklist, that was fine also. You can divide the blacklist between actors, so you have always the same subset of the blacklist that is used by the same actor. So that was easy. Where it didn't work so well was actually for things like the overtaking. Because in the overtaking, obviously, you deal with different cars. So you have different cars, so you have no guarantee that a given overtaking for a same segment will be processed by the same actor. So Akka provides something like it is called distributed data, where you can have shared data between actors. We've tried to do that. It doesn't work very well. And so we had to kind of cheat, and the solution we adopted was actually to create, just for that use case, a specific, a new Kafka topic where the key was actually the segment, the no passing zone. So we were by using a separate topic, we are sure to send actually all the data necessary to check for overtaking to the same actor, and to avoid to share data between between actors that were potentially on different nodes of the cluster. And basically that's it. That's the way this event generator works. So, and the end of my talk. Yes, that's this image. I don't know. It's just if you wonder. And the cool stuff when you work in an hardware company, we needed a cluster to test things, so we started the development on the Amazon Web Services. But at some point, people there say, "Oh, actually, we have all these motherboards from these cameras. We can just create a little cluster." So they put 6. Well, they create 2 towers like this with on each one 6 processors, and you had your mini cluster you could experiment with.
Yeah, thank you very much, Dave. Do you have any questions?
How much time it takes from the moment that, in average, I guess, the moment that you send the event from the camera, the camera, that sent from the camera to, like, the end? I mean, I guess you explained there, like, more or less what you're doing, but what happens after that? You send it to the database? Or?
Yeah, no, well, the thing is, it depends of really the type of offense, but for things that are urgent, it takes it's less than 1 second. Well, it depends. I mean, the slow part really is the part between the camera and the iCar connector, the entrance of the systems. That's really depends on the network, and sometimes we have fast network, sometimes it's very slow. In some cases, the only way they use to connect the camera is to use some, the G4 phone network. It really depends. But once the message is in the system, the event is generated in some 50, 100 milliseconds. That was super fast, and that was one of the requirements.
Yes. What are you using to monitor the throughput and performance of your application?
Yeah, that was that was, I think, the problem was never really resolved. So we never had a really good solution for that. I mean, like a tool able to do that. So usually basically, as long as things go well, that's fine. And when things become complicated, then we had to start looking at logs on the different application and track things. So what we've tried to put in place is actually a way to a separate system that was collecting the logs from the different systems, which was totally ad hoc and made, and provide some extra metadata to document that, and put all the logs at one place so that we could just look at those things. But we really never had. I wish we.
Sure.
we had.
And related, did you experience any stability problems while you were developing or scaling?
No, things went pretty smoothly. I mean. Good. So we had a few bugs. Oh, one thing, actually, yeah, that's, well, it was not really a technical problem. So when we started to deploy the speeding module in tunnels, so it's a tunnel, it's just a long tunnel. You have cameras at each entrance, and every entrance and every exit. And you just measure the speed. And so really we put the thing in place, and it's run for the night, and the day after we look at the data, and we had some extravagant. I mean, the speed limit was about 30 miles an hour or something like that, and we had cars, especially one going at 150 miles an hour or something. So that was really the first deployment. I say, okay, it's impossible to drive that fast. So we had to send the technician, look at the cameras, check everything, etc. Check also the system. Okay, we made a mistake somewhere. And no.
Cool. Thank you.
So, yeah.
We've got to stop there for now.
Okay, yeah, thanks.